Hello and welcome to section 15.3 on conservative vector fields. In this intro video, we're going to go over some terminology that's going to be important for this section as well as a number of things to come later on in the chapter. And so we'll begin here with what are known as simple curves. So these are curves that never cross themselves. So here's an example of a simple curve. Okay, next we have what are known as closed curves, and these are curves where their initial and terminal points are the same. So this curve here in orange is not closed. It does not close in on itself. Whereas this figure 8 curve, okay, it's not a simple curve because of this point right here where it crosses itself. But it is closed, okay, because if I choose a point on the path, then I can parameterize the path in such a way that the initial and terminal points will coincide. And then this example here in purple, this is a curve that's both simple and closed. Okay, simple because it doesn't cross itself, and closed because again I can choose any point on this path and parameterize the path in such a way that the initial and terminal points are the same. All right. So next up we have what are known as open sets, and this could be a set either in R2 or in R3. Okay, so a set is open if for each point in the set there exists a disk centered at that point that lies entirely in the set. Okay, so here's an example of an open set in R2, and this dashed boundary here is telling us that we're not including the points on the boundary. And so because of that, if I choose any point in our region D, no matter how close I am to the boundary, I can always find a disk. The radius might have to be really, really small if I'm really close to the boundary, but nonetheless, I can always find a disk centered at this point P such that the disk lies entirely in the set D. Okay, so that is an open set. Now notice for this set, where I am including the boundary points here. If I choose a point on the boundary, now any disk I draw centered at that point will always contain points outside of this region. Okay, so this set then is not open. All right. Next up, we have what are known as connected sets. And a connected set is a set where if I have any 2 points in the set, then I can connect them by a continuous curve that lies entirely in the set. Okay, so here's an example of a connected set. Any 2 points, A and B, that you choose in this set can be connected with a nice continuous path. Here's an example of something that's not connected, right? So if I have uh, say some component over here and another component over here, right? And these are not connected, right? See, the name is rather relevant or rather appropriate. If I choose, say, a point in this component and a point over here in this component, any path I draw that will connect these 2 points will pass outside of our set. Okay, so this is a set that is not connected. All right, and then lastly, we have what are known as simply connected sets. Okay, so we say that a set is simply connected if every closed curve in our set can be continuously deformed to a point while remaining entirely in our set. Okay, so this is an example of something that's simply connected. So if I draw this closed curve here, this solid blue curve, I can deform this curve in a continuous fashion and contract the thing down to a point while remaining completely within my set. Okay. Now, if I have a set in R2 that has a hole in it, like something like this, and I draw a closed curve around that hole, well, see, now I'm going to run into a problem because if I try to contract this closed curve down to a point, I'm inevitably going to have to pass out of my region due to this hole. Okay, so for that reason, this thing is not simply connected. And if we are looking at sets in R2, let me make a little note here that says a simply connected set in R2 doesn't have any holes. Okay, it turns out that simply connected sets in R3 are just it's more of a subtle condition. I'll just put it that way. and there are some surprises there. Now, if you take a course in point set topology, uh, these are all these are all topics that you would get into in a lot more detail. These are all topological notions here about curves and regions. Okay, so we'll go ahead and stop there. Now in the next video, we'll look at question 1 on the worksheet, which is really just kind of a check-in to make sure we're understanding each one of these definitions. And so for each set, you need to determine if it's open, if it's connected, and if it's simply connected. So you may want to have a few moments to think about each one of these before you watch that video. All right, I'll see you there.